Good morning everyone, I am Mr. Ish. We're looking here at a part 2 video for a subject matter that I've already presented. In a previous video we looked at how we can use integral calculus techniques to calculate the area of an ellipse. We also know the basic definition for the area of ellipse is pi AB. Using the formula area equals pi AB, you can easily calculate the area of an ellipse so long as you know the values of A and B. Why are we presenting these large number of videos before we've actually formally presented videos regarding integration techniques for the variety of functions out there? Simply because we're trying to build an interest here in the topic of integral calculus, and by presenting these videos we can show you the extent and the breadth to the level of integral calculus and how beneficial it can be that once those techniques are learned, and those videos are actually very soon coming in the way. Once those techniques are learned, then these type of procedures will become more meaningful to us. In the previous video we looked at an ellipse equation, then we calculated the area of that ellipse using this formula, then we used Riemann sums, and then we used integration. Here we're going to look at a specific ellipse and we're going to look at it in one of two ways, but they'll both be integral calculus techniques. We're going to look at things here along the dx, integration along dx, and then we'll also look at it integration along dy. What does that mean when we're looking at an area here with regards to an ellipse? In either of these formats, here the equation of the ellipse will have to be presented in the form y equals, here the equation will have to be presented in the form x equals. So if you're looking at a representative ellipse, and you know an ellipse looks something like this, or it could be a vertically directed ellipse, it doesn't matter. What we'll actually look at here is a vertically directed ellipse. But if you're looking at something here in this format right over here, and I'm not trying to identify what we'll exactly look at because that'll become clear momentarily, but if you're looking at something in this form, you know when you're looking at the y equals format for an ellipse, you end up looking at here basically this part right here on the top, and you have to integrate it, then at the end multiply it by 2 for the missing part on the bottom that's not included in this equation. When you're integrating it with regards to dy and x equals format, then we're looking at an equation in this form right over here. Then of course you have to multiply by 2 to capture the area of the other part which is not shown. And likewise you also know from these Riemann sum videos and the previous general integral concept videos that when we're looking here in this format right over here, integration with dx, we're going to have an interval from right here minus x to plus x. When we're looking here and integrating with respect to a vertical line of axis such as the y-axis or a vertical line, here it's horizontal line of axis, here's vertical line of axis. Integrating over here, then we're looking at an interval from minus y to plus y. So these are the things we have to keep in mind. So we'll just get a little shortcut out of the way so that when we're looking at the integration of the areas, basically it will be this form right over here we look at, but in both of these ways for these two forms for this type of an ellipse. Somewhere along the integration process, and you've seen something like this pop up when we were looking at the formula derivation for the area of a circle and the formula derivation for the circumference of a circle. Somewhere along the way we ended up getting something like this. We won't worry about the intervals. We ended up getting this cosine squared theta d theta, and there was some coefficient sitting out over here, and then we used a power reducing formula and we converted in this expression right here to 1 plus cosine 2 theta over 2 d theta. The only reason why I'm bringing it right now is when we actually look at the example, we won't spend time doing this part because we'll already have gone the shortcut out of the way. And then this splits up into two parts along this positive sign. You have something over here d theta 1 over 2. What are additional coefficients are sitting outside will be impacted by this 1 over 2. And then here 1 over 2 cosine 2 theta d theta along with any coefficient sitting out here. When you integrate this by means of its antiderivative, 1 over 2 along with any other coefficients which are sitting outside, you get sine u, and along with upper and lower limit. If these upper and lower limits are things like 0 and pi or 0 and 2 pi, anything for which the sine value is 0, this will always zero out. So when we see this pop up in our equation, I'm only going to focus in on this part right over here because in this example that I'm going to be presenting, very likely this will pop up and this will pop up as well, and this will go down to a path where it will zero out anyway. So when we see this, we'll only talk about this part right here. We won't talk too much about this part, and we'll assume it zeroed out and we won't talk about it. When you do the integration, trigonometric integration technique videos, you'll see exactly why this is a good shortcut to remember. So the equation of the ellipse that we're going to integrate in terms of area is this: 2x squared plus y squared equals 4. We just have to find some parts out of this ellipse simply so we can integrate it. We have to divide everything here by 4, and you know how to do this. It's going to be x squared over 2 plus y squared over 4 is equal to 1. You can rewrite this in the standard form, you know, x squared over root 2 square plus y squared over 2 square is equal to 1. This is a vertically directed ellipse because here the a value is attached with y, the smaller value b here is attached to x. So here I will say a is equal to 2, b is equal to root 2, and it's a vertically directed ellipse. Vertices are going to be 0, comma, plus n minus 2. The minor axis endpoints will be plus n minus root 2, comma, 0, right over here. Plus n minus root 2, comma, 0. So vertices here are 0, comma, plus n minus 2. We don't have to worry about the focal point because it's irrelevant to our question here. And the minor axis endpoints, which are these right here, the minor axis endpoints will be plus and minus root 2, comma, 0. Vertically directed ellipse. If you were to find the area of this ellipse, you can use the formula pi AB is equal to the area. We know A and B is this 2 times root 2 times pi. So the area should be 2 root 2 pi, and that's what we should determine when we integrate this using this procedure dx and when we use this procedure with regards to dy. So this will be the answer. We'll aim for 2 root 2 pi for the equation 2x squared plus y squared is equal to 4. So let's look at this ellipse. We're only looking at here right now with regards integration with regards to dx first. We know that the ellipse looks like this: 0, comma 2, 0, comma minus 2, and then plus root 2, comma 0 for the minor axis and minus root 2, comma 0 for the other corresponding minor axis endpoint. If we have the equation 2x squared plus y squared is equal to 4, and we want to do integration with respect to dx, we have to present our equation in the y equals format. So y is equal to, you can do 4 minus 2x squared and then root it. And you know this is just algebra. When you're looking at this equation over here, not drawn to scale, image would be something like this. And we're looking only at this part right here on the top. But we're missing out the part here on the bottom. Our interval here with respect to dx would be minus root 2 to positive root 2 along the x-axis. Remember, the intervals with respect to dx with the horizontal line of reference must be along the x-axis. Our equation is here along in the terms y equals, and we have that. How would we present our formula over here? It would be this. We're going to do integration from minus root 2 to positive root 2. And then our formula is this: 4 minus 2x squared. By formula I mean our function. Let's use a shortcut over here for even functions. This right here is an even function. This function right here on the top is even function. You can modify everything to be this: from 2, multiplying everything by 2, interval 0 to root 2. And then you have a 4 minus 2x squared dx. There's another times 2 we can do simply right now to calculate and compensate for this bottom part which we are not counting for, which at the end we multiply by times 2. If we want, we can do this times 2 right now and just make it a 4. The 1, 2 coming from this modification of the interval because of the even function, the other 2 coming from multiplying by 2 for this lower part which is not being accounted for by this function, and we've accounted for it. Now what we have to do is just some simplification of this integrand over here. We have 4 minus 2x squared. You can isolate 2. You have 2 minus x squared. Our goal in these type of procedures is to convert this into something which mimics a trigonometric function, as you will learn in a future video. When you do something like this, the 2 can come out as a root 2, and what you have is 2 minus x squared inside. You see, root 2 times this will give you exactly what you see over here, which opens up to that. I've isolated a 2, but the 2 has come out as a root 2. This root 2 can attach with this 4. So what will you get? You'll have a 4 root 2 and then 0 to root 2. And here in the radical, we just have this 2 minus x squared. Basically, for integration techniques, the hardest part normally is just the algebra which comes with everything. Just like as it was in derivatives, the simplification of your derivative is usually more work than the actual derivation part. This is what we have so far. We have to look at something like this based on some trigonometric substitutions which you will learn. A is equal to here root 2. X is equal to root 2 sine theta, and then dx is equal to root 2 cosine theta, all of which you will learn in this upcoming soon video, that how you look at something like this and you see trigonometric aspects in it, which brings you by these substitutions. Since you make a substitution, the intervals change. Theta 1 must be here equal to 0, and you use this formula right over here. X is equal to these interval values. If 0 is equal to root 2 sine theta, theta solving for that is equal to 0. If root 2 is equal to root 2 sine theta is equal to 1, theta is inverse sine of that 1, which is pi over 2. And now all of a sudden your equation, your integral has become 4 root 2, which you already have, from 0 to pi over 2. Has similar procedures as you saw in the circle video. And then here, what you have, this thing gets modified by these substitutions. You have 2 minus root 2 sine theta square, which is just 2 sine squared theta. Sitting outside is this root 2 cosine theta d theta. You can isolate 2 and you get 1 minus sine squared theta, and this is all within a root. You can bring from out of here a root 2 cosine theta. See, the square root of 2 is a root 2. The square root of this cosine squared theta is a cosine theta, because based on a trigonometric identity, cosine squared theta is 1 minus sine squared theta. So all of this part right here boils down to root 2 cosine theta. This root 2 cosine theta can multiply with this root 2 cosine theta to give you 2 cosine squared theta. And this is going to the shortcut that I was talking about at the beginning of this video. So from all of this expression, we're getting 2 cosine squared theta d theta. This 2 can come right outside right here with the coefficient, and you get 8 root 2 from 0 to pi over 2 cosine squared theta d theta, which we now know, and the shortcut as I was talking about will lead you by means of that power reduction formula, 1 plus cosine 2 theta over 2. All of this coming into this play will separate into two forms, which I was telling you. One form will zero out, and I showed you why at the beginning it will zero out, and we'll only focus only on the first part, separating everything around the integral and focusing only on the first part. We have 8 root 2 sitting outside divided by that 2. Remember I was saying that 1 over 2 will multiply with whatever coefficients are already in place. 0 to pi over 2, and we have d theta. The remaining part over here I'm not talking about because it zeroes out. We're only focusing over here. The antiderivative of this d theta is just a theta, affected by pi over 2 and 0, and we have here 4 root 2. Remember, divided by 2 is a 2 is a 4. 4 times that root 2 is a 4 root 2. When you integrate this by procedure that you will learn, you'll have 4 root 2 times pi over 2. This cancels out with this 4 to give you 2, and you get 2 root 2 pi as being the area, verifying what we already know using the basic formula for an area of an ellipse. But we've done this now using this, the dx, with regards to presentation along an x-axis and the intervals along the x-axis and the equation y equals format. I've already taken care of the fact that we have this shortcut playing with the times 2, and then that lower missing part multiplying by times 2 to give us this 4, which has played all the way through anyways. Now what remains in the remainder of this video to look at things here with respect to dy and the equation x equals format with a vertically oriented interval, lower limit, upper limit, and we should arrive at the same answer. So in the last segment of this video, we're going to be looking at the same ellipse, 2x squared plus y squared equals 4. We already know the area is 2 root 2 pi, but this time we're looking at things here along a vertical line of axis or vertical orientation. We're going to integrate with respect to y, dy, integration with respect to dy, and our equation must be presented in the x equals format. If you look at the major axis and the vertices, you have 0, 2, 0, minus 2. These y-axis coordinates, minus 2 to 2, define the lower and the upper limit of that interval. Remember, in the previous form we had minus root 2 and positive root 2 along the x-axis. Here we have to look at things along the y-axis. So minus 2 and 2. That will be our interval. What we're really looking at over here is this equation right here. 2x squared plus y squared equals 4. We have to present in the x format. So x will equal to what? 4 minus y squared over 2 root. This will become our equation. You're just taking that equation and you're solving for x. What does that do over here? We end up looking at something like this. So we're not looking at an even function, so we can't really modify our interval. Our interval will be just minus 2 to 2. We can't convert it to 2 times 0 to 2. We have to just keep it minus 2 to 2, which is fine. We can deal with that. This is our equation which will go to that. Our equation will be like this. Minus 2 to 2, we have 4 minus y squared over 2 with respect to dy. This over 2 is all under the radical. The best thing you can do over here is simplify this part right over here, and we'll do that right here off the side. Using the properties of radicals, this expression is the same thing as looking at as this. You can separate it along the denominator, and then what you're really doing is looking at 1 over root 2 times 4 minus y squared. And what we want to do is look at things along this perspective now. 4 minus y squared over root 2. What we'll do is in the next sentence, we'll make the adjustments. So our area becomes this 1 over root 2 being pushed outside, the coefficient being pushed outside, and then 4 minus y squared dy. So from this step over here, we have to recognize that there's a trigonometric expression hidden in terms of this radical expression. That's recognition procedure, something you learn in a trigonometric integration substitution video in the future. And when you see something like this, you start thinking of these things. A is equal to 2, y is equal to 2 sine theta, and then dy is equal to 2 cosine theta d theta. These recognition procedures you will learn with practice. And then since we're making substitution, these intervals will change, theta 1 and theta 2. We have to look at that. And everything is based off on this. Why are these values? These are y values. If 2 sine theta is equal to minus 2, solving for that theta, you get a minus pi over 2, because sine theta is equal to minus 2 divided by 2, which is a minus 1. Inverse sine of that minus 1 is a minus pi over 2, or 270, but we keep everything as minus pi over 2. Likewise for this, 2 sine theta is equal to 2, sine theta is equal to 1, inverse sine of that 1 is a pi over 2. Now our expression becomes this. Our integration expression becomes minus pi over 2 to positive pi over 2. And we have 4 minus y squared, which is 4 sine squared theta. dy becomes 2 cosine theta, 2 cosine theta d theta. We can erase this. When you look at this expression over here, you can isolate 4. You have 4 parentheses 1 minus sine squared theta. All of this in a radical, this entire expression. This entire expression can boil down to square root of 4 cosine squared theta by using trigonometric identity that you know of. When we come right over here, we have 1 over root 2. We're bringing all of this expression right up over here. We have 1 over root 2 integral minus pi over 2 pi over 2. This entire expression, 4 cosine squared theta, is a perfect square. It becomes 2 cosine theta, which multiplies with this 2 cosine theta, give you d theta. Remember here in this specific example, we have to multiply by 2 at the end to capture this part right here, which is not being accounted for, this other half. I didn't bring that in over here, but we can multiply our product answer here with the times 2 at the very end. This 2 cosine theta times 2 cosine theta will give us what we were alluding to at the very beginning. We'll get 4 cosine squared theta. This 4 can be brought right outside over here, and it can be attached. See, now you're seeing this cosine squared theta, which would split up into 2 parts. The second part I'm not going to look into because it would zero out. You would have this 4 over root 2, and then minus pi over 2, and pi over 2. You'll have d theta over here. You can refer back to the beginning part of this, because this power reducing formula will come out as 1 plus cosine 2 theta over 2. I'm only looking at this part right over here, 1 over 2. This 1 over 2, this 2 has to multiply with right over here, 1 over 2, you get 2 root 2. Another thing we can do is account for this 2 times 2, which we have to do at the end, and might as well just do it right here. 2 times 4 divided by 2 root 2. This is a times 2 coming right over here. This over 1 over 2. 1 over 2 is coming from the opening of this via a power reducing formula. We can cancel these 2's out. We have 4 over root 2, and we have to integrate this. When we integrate this, we have 4 over root 2. We have a theta from pi over 2 to minus pi over 2. When you integrate this using the technique you will learn, you'll get 4 over root 2 times pi over 2 minus pi over 2 is a pi over 2 plus pi over 2, which is just a pi. You end up getting a 4 pi over root 2. You can rationalize this, root 2 over root 2. You get 4 pi root 2 over 2. Simplify this. 4 divided by 2 is a 2. 2 pi root 2, and you get 2 pi root 2, which is the same thing as 2 root 2 pi, and that's the area of this part right over here, this ellipse, using a vertical orientation in terms of integration. So in this video we've shown you for this ellipse we can integrate along an x-axis dimension using dx, integration with respect to dx, and now vertical with integration with respect to dy, and you've seen both of those procedures play out for this representative equation, corroborated by the area determined from the area of an ellipse formula, pi ab. That's it for this video. I hope you enjoyed it and it proves to be educational for you. Thank you for watching. Have a nice day.